Biomech Probs, Finding Jump Length, a series of biomech talks. For this biomech problem, we're going to find the overall jump distance for a long jump with these conditions: a center of mass vertical velocity of 2.8 meters per second, a center of mass horizontal velocity of 9.5 meters per second, both of those being at final contact of takeoff, a takeoff distance of 0.5 meters from the scratch line to the center of mass in the x direction of final contact, and a landing distance of 0.5 meters, which is the center of mass in the x direction at initial contact to the last mark in the sand. And then finally, the height of the center of mass at final contact is going to be 1 meter, and the height of the center of mass at the initial contact of landing is going to be 0.5 meters. And don't worry if you didn't catch all that, we're going to draw a really good picture. This example, we're going to be calculating long jump distance, and this is going to give us a sense of what our elite athletes need to achieve in order to jump their desired distances. As per usual, we're going to be using our digital engineering paper with our problem-solving process, which you can check out in my previous video. We always start by filling out our header with our name, the name of the class, the assignment number, and the problem number, as well as the date and the page number for our assignment. To solve this particular problem, we're also going to need access to projectile motion equations. Typically, professors will give these equations to you on an exam. We're going to be using the ones defined above in the vertical and horizontal directions. The VF is going to stand for final velocity in meters per second. VI is initial velocity in meters per second. Acceleration is going to be in meters per second squared. Time is in seconds. SF stands for final displacement in meters, and SI stands for initial displacement in meters. We're going to start by filling out our problem statement, which is to find long jump distance measured in meters. Then we'll fill out our assumptions, which in this case is assuming that the acceleration due to gravity is going to be equal to negative 9.81 meters per second squared. Then we can fill out our knowns, which we outlined on that first page. So we've got center of mass vertical velocity, horizontal velocity, A1 and A2, which are going to be those distances in the horizontal direction at the beginning and end of the jump. And then SI and SF, which are the vertical positions of the athlete at final contact of takeoff and initial contact of landing. We started our problem statement a little bit lower on the page because I know that the figure is going to take up a lot of horizontal space. And then we also need information from our equation sheet that we mentioned before. So we have 3 equations, 1 in the horizontal direction and 2 in the vertical, that we're going to be using to solve this problem. Next, we're going to draw a great figure so we get a better understanding of what is happening in this problem. So we have our jumper who's going to be starting at a specific horizontal and vertical distance relative to the board, and then they're going to act as a projectile flying through the air before they land in the sand on the right hand side. So our total long jump distance is going to be measured from that yellow board to the last position of the jumper in the sand. We're going to add our A1 and A2, which were given to us, and these are the length from the center of mass to the scratch line, and then the length of the center of mass to that last position in the sand. Our jumper is starting at a 1 meter height above the ground at final contact of takeoff, and then they're going to be landing with the center of mass position 0.5 meters above the ground at that landing. And then we're also going to add in our center of mass vertical and horizontal velocities at that final contact of takeoff. We also want to take note of where the initial horizontal distance of the center of mass is on our diagram, which is going to be labeled with that SIH, and also the final position of the center of mass, which is labeled with SFH. Alright, and now that we have that all set up, we're ready to start solving our problem. So we know our total long jump distance is going to be equal to that final center of mass position minus the initial center of mass position plus the A1 and A2 distances to get that total long jump distance. And we also know that our initial horizontal distance is equal to 0. We're going to define that as our 0 point. So in order to solve this problem, we know all 3 of those variables, but we don't know SFH yet, so we don't know the final position of the center of mass. So in order to find that, we're going to use the equation in the horizontal that we have in our equation list, and we can see from there that we know everything in this equation except for we need to find that final horizontal position of the center of mass, and we also need to know what the change in time is. So since we don't know two variables in that equation, we need to next figure out an equation that's going to help us get that change in time. So looking at our other equation, we have the final vertical velocity equals to the initial vertical velocity plus the acceleration times the change in time. And we know the initial vertical velocity, and we also know the acceleration due to gravity, but we don't know what the final vertical velocity is equal to. So then we need to go to one more equation where we know everything except for what the final vertical velocity is going to be equal to. So now we've figured out our approach with our equation, so we can begin to solve. So using that last equation, we're able to plug in all of our knowns, so the vertical velocity initial, the acceleration due to gravity, and also the position of the center of mass at the initial and final points of the jump. And when we plug all that into our calculator, we're going to get a value of 17.65, and then we need to take the square root of that, which is going to leave us with either plus or minus 4.2 meters per second. However, we know in this example, when the athlete's landing, they're generating a downward vertical velocity at that initial contact, so we're going to use the negative 4.2 meters per second value. Then, once we have that, we can also find change in time using our other equation. So we're going to plug in that negative 4.2 meters per second and set that equal to 2.8 meters per second, which was our initial vertical velocity. And then we know the acceleration due to gravity, and we're able to rearrange that equation and solve for the change in time, which is going to give us a value of 0.714 seconds. And now we're getting really close, so we know our change in time, and we can use that to find the final horizontal position of the center of mass. So plugging that into our equation, we know that we started at a distance of 0 meters, which we're using as our reference point. Then we're going to add the horizontal velocity, which was 9.5 meters per second, multiply that by the change in time, and we're going to get a final center of mass displacement of 6.78 meters. But this isn't what our question asked for. Our question wanted to know what was the total long jump distance. So in order to calculate that, we also need to factor in the distances of A1 and A2. So if we plug that into our overall equation, we can see that our total long jump distance is 7.78 meters. And if we think about the speeds that the athlete is coming in with, this distance makes sense and is on par with something that an elite jumper would be able to achieve. So hopefully talking through this problem gives you a better sense of how athletes are using center of mass velocity and then acting as a projectile to generate long jump distances. A series of Biomech talk, Biomech Probs, finding jump distance.